To keep a drone airborne, its onboard computer must constantly translate chaotic variables, like sudden wind gusts, into precise mechanical commands. Early-stage aerospace testing requires complete transparency in decision-making. If a neural network makes an unexplainable choice during a flight test, a 50-pound aircraft becomes an unpredictable kinetic hazard. Engineers solve this using a finite state machine, or FSM, defined by a 6-tuple equation. S represents states, E stands for events, G are guards, A represents actions, T defines transitions, and S0 is the initial state. By forcing the software to operate within these parameters, engineers eliminate the ambiguity of black box models. The system reacts the exact same way to a given input every single time, creating a deterministic logic that remains stable regardless of external chaos. The software team for the AirGuard drone project is using this methodology to build their initial flight logic. The team calls this iteration Phase 0. It is a minimal architecture designed to establish a testable baseline before advanced features are added. The core design priorities are clear, verifiable state transitions and safety-first behavior. To prove the system's reliability, the team must first map the ideal flight path and then test the architecture against specific hardware and environmental failures. This standardized baseline allows the team to verify safety protocols before adding complex multi-waypoint operations. The model starts with scenario S0. This represents the nominal mission flow: a startup, a flight to a single waypoint, a brief hover, and a return home. We can trace this flow on the FSM's node and edge graph. The starting parameter, S0, is the safe off state. In this state, motion is blocked and the motors are disarmed to ensure safety on the ground. The drone then runs diagnostics on its GPS, battery, and radio links. When those checks pass, the logic steps through the pre-check state and moves into ready. A manual arm command from the operator triggers the arming sequence, which verifies propulsion readiness before landing in armed idle. A takeoff command initiates a controlled climb. Once the drone reaches mission altitude, it transitions into active navigation in the go-to-waypoint state. Upon arrival, a timer dictates the duration of the hover hold before the system automatically transitions to return home. A controlled descent triggers landing, and touchdown detection initiates disarming. This shuts down the motors and routes the logic back to safe off, completing the mission cycle. This closed-loop graph proves the nominal flow operates as a deterministic cycle under ideal conditions. Hardware faults and environmental failures are inevitable in aviation. The Phase 0 architecture must account for these threats to maintain safety. Scenario S5 simulates a pre-flight failure, such as a missing GPS lock or a low battery. If a pre-flight check fails, the FSM diverts the logic into a separate safe ground state and blocks the transition to ready. These ground logic parameters physically prevent the system from arming. Because the required transition states are unreachable, the drone cannot move toward takeoff. This is architectural prevention. The system maintains safety by structurally forbidding dangerous states from ever initializing. The software must also manage mid-air anomalies while the drone is active. Scenario S1 occurs if the battery drops below the safe mission threshold while the drone is navigating toward its waypoint. Onboard guards continuously monitor sensor thresholds. If the voltage drops too low, a guard will sever the path to the next mission objective and force a transition directly to return home. Scenario S4 handles GPS degradation, where navigation data becomes unreliable mid-flight. The FSM suspends navigation and shifts the system into a temporary degraded nav/hold state. This state uses dual exit logic to give the system time to react. It can either recover a clean signal and return to navigation, or escalate to an emergency sequence. These intermediate failure states allow the system to degrade gracefully, providing a buffer that prevents a sensor glitch from causing an immediate mission failure. For critical failures, the FSM uses global interrupts, high-priority safety rules that override the current mission state. Scenario S3 represents a severe onboard fault, like a propulsion failure. The architecture groups all airborne states together. A critical fault can hijack the system from any point in the flight, routing it directly into an emergency land sync node for an immediate shutdown. Scenario S2 involves a manual abort command from a human operator. This similarly interrupts any autonomous state, routing the logic into a distinct abort state and handing authority back to the operator. Manual overrides and critical hardware faults strip control away from the mission logic. These pathways are designed to be one-way transitions to ensure safety. These hard-coded sync nodes act as the structural floor for the drone, ensuring it always has a predefined recovery pathway, regardless of the fault. The complete Phase 0 state diagram maps all potential inputs to predefined outcomes. The blue spine represents the nominal mission, the intended sequence of events. Surrounding that sequence is the failsafe logic. These yellow and red pathways are integrated into every stage of flight. This structure provides predictability. Every possible state is accounted for, and every transition is mathematically bounded. Actual aerospace safety is built on these deterministic boundaries. The system's reliability comes from its inability to enter an undefined state. The Phase 0 architecture serves as the structural foundation for all future iterations of the AirGuard software. Next, the engineering team will refine fault thresholds and add support for multi-waypoint missions. Long-term goals include integrating obstacle awareness and advanced recovery logic into this core FSM framework. By securing this testable baseline, the AirGuard team creates the necessary framework to safely scale toward full autonomy.